Okay, in this sample problem, we're going to look at how we can convert linear momentum to angular momentum for an object that's initially moving with some linear momentum and then attaches onto an object that causes it to begin an angular momentum path, or a rotational path that has an angular momentum. Okay, so here we have a particle mass m. It's traveling at a speed v, and it strikes a light rod. And so as soon as we say light rod, negligible mass, meaning we don't have to account for a moment of inertia for the rotation of the light rod, at a distance r from a point of rotation. So let me make this my point of rotation, and here's my light rod. And I have a mass traveling with some mass at some speed v, and it's going to strike this rod, and then that rod's going to be set into rotation, right, due to this initial momentum of the ball or the mass that's striking it. Now, the lever arm for this rotation is the vector r, and I apologize, my v's and r's begin to look the same. We want to know, once this object starts rotating, what's the angular momentum of the particle on the rod. All right, so angular momentum, L, will be the moment of inertia of the particle about its point of rotation times the nu omega, or the angular velocity of the rotating mass with rod. Well, if I have a rod of negligible mass, I have to figure out, well, what is my moment of inertia? So remember, moment of inertia is the sum of all the mr squareds, and in this case we have a single mass m at a radius r away from the point of rotation. So the moment of inertia for this rotating object is just mr squared. Now, it's traveling with some initial p, which is equal to mv. Now, as soon as it begins to rotate, this v becomes the linear speed of the particle on the edge of the path of rotation. And what we know is, for rotating objects, that v is equal to r times omega, which we've seen many times before. So I can rewrite this as omega is v over r. Okay? So now let's go ahead and substitute. So we know that I is mr squared, and omega is just v over r. And when I multiply r squared over r, I get that the angular momentum now of this particle and rod rotating is the initial momentum mv, right? That's the initial p, times the radius of the rotation r. And this is how we can look at a linear momentum converting into an angular momentum due to the mass beginning its rotation on the rod. Now, if we had a rod with some kind of mass that had a moment of inertia, we would have to add that to the I here, and that would change our I, and then we would have a different outcome. But with a light rod, where this mass is the only mass providing the moment of inertia, it becomes MVR.